it didn't leak.
Stand
And
by.
all
Oh,
right,
I think we're launching the show, guys, in the
you got
rain.
it.
It is time. Let's do it, gentlemen. We've assembled again on screen for the SBAU Astro Hour. Ladies and gentlemen, it's a 1 hour weekly vlog, Monday mornings. We do live 11 to noon from our men caves and computer dens with the Santa Barbara Astronomical Unit, South Central Coast Longtime Telescope and Astrophysics Club. We're pushing 70 years. You know that next year? I'm your host, Ron Herron, who, as vice president, learned a lot from my very knowledgeable comrades at SBAU, and I'm going to learn about telescopes this hour. I'll introduce you to the rest of the Brain Trust here in a moment. You can watch us live on YouTube, almost live, 20 seconds. Come to our first Friday meetings. We had a great one this past weekend where we have great speakers. We went up to Mount Wilson via PowerPoint. Santa Barbara's Museum of Natural History. We were in Flashman Auditorium. Come check us out on sbau.org. Watch us on YouTube, as I said. You got questions, come to our outreach events, including our second Saturday Star Party, which this nasty weather will be gone by this coming Saturday night, ladies and gentlemen. We expect to see you out there along with the hundreds of others. This week, February 5th through the 11th, 2024. It's our 155th program. By the end of the month, March, we'll start our 4th year on the air of the Astro Hour. Let's let me tell you what we're going to talk about real quick. I'm going to learn about the instruments, the tools of science that we have in the club. For those of you thinking of buying a telescope, you're going to learn about it this hour. Where the Auriga, the charioteer, is up in the sky in winter. We're going to learn that. Comet 12P, Pons Brooks, is up there getting through the Swan near the Horse. The moon's pretty much gone, or will be. We should find asteroid 4 Vesta and the Crab Nebula this week when the sky gets a little clearer. Going to focus on Messier 17, the Omega in the Swan Nebula up above the Teapot asterism. Let's find out what's going on and talk to the gang right now, ladies and gentlemen. My name's Ron, and here is Jerry Wilson, our president.
Good morning.
Jerry?
Good morning.
Everybody was pretty much at the meeting last Friday night, including your lovely wife, Pat Forgy, big supporter of you and me, your wife, and 7 years as president, recently reelected. Here's Chuck McPartland, our outreach guy. He is awesome. No more secretarial duties, but your wife has got a second job. She's now the treasurer as well as merchandise manager. I'm about to buy another jacket to get this one. I can't seem to get this one totally clean. And you know, they charge more at the cleaners to clean this sucker than the cost.
Yeah.
Yes, I know that.
Yeah, anyway, Chuck's married to Pat McPartland. And here's Tom Whittemore, editor of our SBAU monthly newsletter. I'm going to try to talk him into publishing a photograph of the legendary Astronomy Magazine columnist this coming March, because that's going to be our speaker on the first day of the month. He's married to Maureen, used to work at Westmont College. We have with his cat, which one is the cat? He's been blinded there. There he is, Tim Crawford, resident lens telescope expert.
That's bamboo.
Yeah. I hope you're going to learn something. Maybe not. You may know everything about telescopes that Jerry's going to tell us here. Married to Karen, who's having a birthday. Bless her heart.
Yep.
Take her
Happy
to some
birthday, Karen.
All right. Well, if you can't take her out, it's because of the rain, but later on you can. And doggone if Bruce Murdoch hasn't joined us. Longtime supporter, telescope enthusiast, and quite an intelligent man. He's also president of the Santa Barbara Theater Organ Society, who's married to Bonnie. Let's get it going. Number 155. Jerry, he sends us these silly cartoons based on science, and here we go. This is the two monsters, and I wrote this one down. Is this okay?
This is good.
Here we got a typical earthling ready to go into the water with a stupid little inner tube around, and they're coming in close, looking out the window of their spacecraft. Aliens go, we're searching the universe for intelligent life, fella, but come on, where's the next closest planet? We're not going to stay here for this. Is there intelligent life? Take me to somebody. Ah, the dog, the white dog at the table with the girls. my girlfriend telling her friends how perfect our relationship is, and me knowing that nothing can be perfect because of entropy and the second law of thermodynamics. That would be the dog talking.
But he's being censored there, as you can see. That's
Oh,
a
is that
position
right?
I frequently do with my dog when people come up.
It looks like a nice dog. Is the dog
Oh,
the boyfriend or the?
it's a Irish setter, a white Irish setter.
Well, that's a boyfriend. That's as good as they get. That's all girls. Okay, at the table. Here are the two vintage ladies talking. This is the latest from QAnon, everybody. Next time a conspiracy theorist tries to tell you what really happened, present a more outlandish theory and accuse them of covering it up. She says to her, the moon landing was faked. And the other one says, yeah, you believe in the moon.
I like that, yeah.
There's no stinking moons.
The moon is faked.
Wonder who they're going to vote for this fall. All right, here's the guy on the street, bald guy at a payphone, say, my smartphone and my smart car just drove off without me, laughing. Ah, ha, ha. Score one for A&I.
Pretty good.
Artificial intelligence. All right, is this somebody at okay, it's a scientist. It's not Einstein. Oh, it is Einstein.
Hmm.
He discovered that time equals money. I've always wondered about that. Time is money. What is the formula, though? Can anybody tell me?
They're just nonsense formulas.
Yeah.
$sign equals
They're
whatever.
just squiggles. They're not even real figures.
Ah, here's a crashed weather balloon. Not quite, but it's obvious these two aliens are looking out, having hit the
There's a
desert.
flying saucer, the front end is squashed because they crashed.
Well, naturally, at the bottom it says there was a bit of skepticism among the media regarding the official Air Force explanation. They're saying, just a weather balloon. That's what we are. Okay. Oh, this was the one we had earlier. The one you missed from last week? The backyard, the backyard table, periodic table for your patio.
Oh, I thought I had shown that last week.
I know you showed it. It had the lanthanide series at the bottom. It was one of the seats of the bench.
Yeah, someone asked me about that.
Okay, maybe I must have missed it. There was something else about the periodic table. You did the new element was UM.
Yeah,
that was the element of uncertainty.
Yeah.
Okay, yeah, right. All right, you want to teach us all about telescopes? Even though you're preaching mostly to the choir, I'm the guy that's going to learn. Make that a little larger if you can. That's as big as it gets.
Well,
I like this. This was very nice.
It'll start going off the edge.
Oh, you're right. It will.
So this is a timeline for the history of telescope of development and related topics that I found on Wikipedia. It's very nice. It shows that even as early as 400 BC, roughly then, Chinese philosopher Mozai recorded the observation that concave mirrors can focus the rays of the sun. And you'll recall that back in ancient Greece, there was someone who was reported to have burned up incoming hostile ships with large mirrors, copper mirrors. They were either a large number of flat ones or concave mirrors that focused the sunlight. Not a lot of proof of that. It's more of a legend than recorded fact.
In the Mojave Desert or on the way to Las Vegas, there's a big
big what?
solar
array.
I think he froze. But yeah, I know the solar array he's talking about.
Mm-hmm.
And it's a lot of flat mirrors focusing on a tower where the heat builds up and moves fluid around.
Molten sodium, I think.
Yeah. You froze for a while, Bruce.
Pardon?
You froze for a lot of your talk, so we filled it in.
All right.
But good observation.
You want to finish your thought, Bruce?
Say again?
You want to finish your thought, or we missed it?
No, I said out on the way to Las Vegas, you pass just before you go through the California-Nevada border, you come to a large solar farm. It's got 4 towers, and it's not operational anymore because it costs more money to run it than they make from it. But when it was operational, the heliostats, a whole bunch of little mirrors down there that focus the sun up to that central heat collector, birds would fly through it and they would burn. And they called them flamers.
Yeah, I remember that.
Wow.
So anyway, back in also 400 BC, Greek playwright Aristophanes recorded that glasses of many shapes are filled when they're filled with water, they can bend rays of the sun.
That's an interesting one. That's a really interesting one right there, Jerry.
Yeah, these things, when you first hear about the Hans Lippershey in 1608 filing the first patent, you think that there must have been a background of some kind of experimentation or dabbling or observation. And someone has researched that quite a bit and put these things up on Wikipedia.
Yeah.
But the mathematician Euclid first wrote an overview of the sun's rays reflection and refraction. His work was expanded 5 centuries later by Ptolemy. So in the 10th and 12th century, several Arab scientists start examining the properties of light, mirrors, lenses, and more. Ibn al-Haytham's book of Optics arrives in Europe and was later translated to Latin. It became the foundation of modern European exploration of lenses. In the late 13th century, the first recorded spectacles were invented.
Jerry, can I get one thing clear for the benefit of the folks like myself that don't know much about this? The two words convex and concave. Concave I've got down to be the way a mirror is shaped. It's
each one of them can be a mirror. Concave is just like a cave in the side of a mountain. It's a hole going in. So convex is a beer belly.
It's indented like a beer. Yeah, right, like a bowl. Convex is what you see in magnifying glasses, right? That's the early telescopes were convex, bulging, if you will, glass.
Yeah, double convex.
Okay, and so that's what we're dealing with: concave, convex.
Well, also, Galileo's some of his eyepieces and things had both concave and convex.
Really? Well, were the concave used as mirrors?
We'll get to all those when we have drawings. Let's just get the word history out of the way here.
Okay, got it.
So, 1570s, several reports were made of the abilities of combination of lenses to make distant objects look as if they are near. And then in 1608, the Dutch spectacle maker Hans Lippershey filed for his patent in the Netherlands. Other Dutch scientists, Metius and Janssen, also tried to register their own inventions for a telescope.
Those two guys, Jerry, I think Metius and Janssen, I believe that they kind of bickered and fought between each other for the patent, and the patent office said, "Okay, neither one of you are getting it," and that's when Lippershey came up and he took over there, and then and of course Galileo stole everything.
Well, Galileo bought got a hold of the patent, and then he built his own. Now, when they he called it a he called it a something. He used his telescope to make many significant astronomical discoveries. Now, when they made telescopes, they didn't have any way of testing the shape of the surface, so they would just do this thing that was known to cause a bulging or an indented surface, a convex or a concave surface, and they'd make a bunch of these things, and then they just use them. They'd look through them, and they'd start putting a diaphragm in front of it to reduce the aperture until it formed a good image. And if it was still close to the size of the original lens, then they'd keep it. Otherwise, they just remelt it and start again. So they just mined the result for the good ones.
That's how Herschel made some of his really high magnification eyepieces, was by dripping molten glass into water and then taking the various droplets and trying them out.
Yeah.
So did they have magnifying glasses at about the same time, or did they come earlier or later?
No, they did. They had magnifying glasses at this time.
Okay.
We had Leeuwenhoek, the guy that made the microscopes, and he used a metal plate or something like that with a hole in it, and he put a drop of water on it.
Oh, yeah, for a lens, yeah.
For a lens.
And it froze or what?
No,
No,
just
you look through
as
it.
long as you didn't wiggle it too much, it worked.
No kidding.
So the first person to use the name telescope was a Greek mathematician, Giovanni Demisiani, during his visit to the Italian Academy of Science. Let's see this. Okay. Johannes Kepler in 1611 provided detailed scientific explanations about the inner workings of telescopes, optics, and light rays. He created the first telescope that was focused only on astronomy. It had 2 convex lenses. Now, these were plano convex lenses. That is, they were flat on one side and bulging on the other. In 1616 to 1684, large amounts of scientific effort were focused on further development of the telescope, including the invention that provided by Christian Huygens, James Gregory, Isaac Newton, Laurent Cassegrain, and Robert Hooke. English mathematician John Hadley managed to significantly improve telescopes by shifting to parabolic mirrors.
Mm-hmm. Mm-hmm.
In 1870,
he did ray tracing to try to discover that parabolic mirrors were the right thing to do.
Yes. Math back then was to a large extent geometrical, and a lot of these ray tracings were popular. Telescopes.
You draw a tangent to the curve, and then you draw the normal to that tangent, and then you incoming and outgoing have to have equal angles.
Right. It's easier for mirrors than it was for glass, for lenses.
Mm-hmm.
So then we start on an improvement cycle of making bigger and better telescopes. 1845, Lord Rosse at Birr Castle in Ireland had the largest reflecting telescope at the time with a 72-inch mirror, 6-foot diameter mirror. 1897, Yerkes Observatory built the largest refracting telescope of its time at 40 inches or 101.6 centimeters. And
how many tons that weighed?
I think he mentioned that at the last Friday's talk, but I don't recall it.
Well, I was wondering that last Friday's talk is going to be up on the website soon, is it not?
Yes.
Because I want to watch that again.
Yeah, it was very good, very informative, especially the thing about sunspot cycles on other stars that he had. That was extremely.
Oh, yeah, yeah. Well, I didn't really. I knew that these telescopes where they combine the outputs from they get what is this called, a simulated or a where they get
interferometry.
Yeah, right. So they can get much higher spatial resolution.
Right.
They don't get any more light, but when you're looking at a star, you don't. Well, I guess you do need more light, but I thought that was very interesting.
Yeah, no, they were looking at the brighter stars.
Yeah. Oh, of course. Yeah.
They're seeing sunspots on distant stars?
In general, yes.
The shapes.
They didn't resolve the sunspots, but they looked at the total brightness change, so they could see the sunspot cycle.
They detected sunspots.
Yeah, the existence of sunspots.
And this was Mount Wilson.
A lot of places, but he showed the data from Mount Wilson, yeah.
Gotcha, okay.
So in 1910, one of the most famous telescope designs is created, and this is the Ritchie-Chrétien telescope. Ritchie-Chrétien tried to get the Mount Wilson and the Palomar observatories to use Ritchie-Chrétien designs instead of Newtonian design, and he was fired. Ritchie was fired for that. So the 100-inch Hooker was built on Mount Wilson in 1917 and became the biggest telescope in the world. 1948, the 200-inch on Mount Palomar became the largest. And from then on, pretty much all the big stuff that goes up is Ritchie-Chrétien design. It's the most popular design among professional telescopes. First gamma ray telescope ever to be used in 1970 aboard the Uhuru satellite. 1990, the Hubble Space Telescope went into Earth orbit. In 2009, the Kepler telescope was launched into space with a 2.4 meter diameter mirror, about 100 inches, about the same size as the Hooker telescope on Mount Wilson. And in 2021, NASA launches the James Webb Space Telescope with a staggering 6.5 meter diameter telescope.
The only thing that I would add is maybe that Ritchie wasn't fired because he wanted to use the Ritchie creation design, but he was kind of being a pain in the butt about the mirror, the Hooker mirror, because it had so many bubbles in it. And I think that his bitching and moaning, Hale finally had enough, and he said, "Okay, I'll tell you what, go work on something somewhere else."
Yeah.
Bubbles don't matter, do they? As long as they're down in the glass. And
Yeah,
not at the
it turns out it doesn't matter. You're right.
It doesn't matter, but Bruce, he was kind of being a pain in the butt because he was a perfectionist.
Okay, so these are a brief survey of the most popular telescopes that are used today, and mostly that are available to amateurs. There's a few things, such as a Schmidt camera and a Schiffspiegler telescope, that I'm not going to include in any of this. But this is a simple basic telescope, the first use of lenses. And you see it's a simple objective lens. What's represented here is a single piece of glass that's curved convex on both sides. It's a double convex, not a plano convex. And then an eyepiece here. So the objective lens produces an image here, and this eyepiece lens acts as a microscope and examines the miniature image produced by the incoming objective. This is the telescope's focal length. This is the eyepiece focal length, and dividing the two together gives you the magnification, the power of the telescope.
So would it be fair to say that Van Leeuwenhoek came along and invented the microscope to look at little things?
Yeah.
And that they're set up this way, aren't they? Convex only. You don't have a mirror and
it was a single lens. It was a very, very short focal length lens.
Yeah. As Chuck pointed out, one person, Huygens, I think, made his short focal length eyepieces by dropping molten glass into water, and it forms little round beads. And that's what he'd use here for an eyepiece, is a little round bead.
Oh, really?
So Van Leeuwenhoek used this lens, and this was the slide that he was looking at. But here in a telescope, we're producing the image by a bigger lens out here.
Oh, how interesting.
Now this lens out here, this particular kind of lens suffers tremendously from false color, because the glass has a property called dispersion. And the line that this goes through up here, like just a beam of white light going through a prism, it expands it into a rainbow of colors. So you get and so that means that each color comes to a different focus. So if you look at the image here with these simple lenses, only one wavelength will be in focus, and the rest will be surrounding, the out of focus light will be in a haze around there. So that's chromatic aberration. And in order to get away from that, the first generation of telescopes, they made these things very long. For example, this focal length here of a single lens like this was sometimes up to 100 feet long or 140 feet long. Very ungainly, but it minimizes the chromatic aberration, so you can get a more color-free image. But it turns out there are better ways to do that.
And those really long lenses, they actually would just put the lens by itself up on top of a pole, and then the eyepiece was held, and it had a cable that went up to the top of the pole, and you would pull the cable tight, and then it just move around until you saw the image that was coming from the lens. So it was really hard to use.
Very hard to use.
110-foot soda straw.
Yeah, so it's very narrow field of view.
It's similar to
the earth turning.
Are you saying it's similar to what a prism does?
It's exactly the same as what the prism does.
Yeah, if you look at the cross-section of the lens, Ron, near the edges, what you have is a prism.
Yeah, if you cut it off here, then what you've got is a prism. So this lens spreads it out into its spectrum of colors down here, and this one spreads it out into its spectrum of colors going up there.
And
they all come to a traffic jam right here.
And Ron, I'd like to add here that the colors, each color, it has a different wavelength, an actual physical length. And so that physical length is what puts them all out of focus in one place and in focus in another.
Yeah, it's a property called dispersion. And they just knew the words glass. They didn't even know at this time about crown and flint glass, which were when they started discriminating against different types of glasses. They found out they could make, I think Fraunhofer came up with the idea of, or the ability to make different types of glasses with different dispersion relationships. And so with curvature and different glasses, one lens will spread the light out in colors, and the next lens right behind it in an achromat would put the lights back, would put the colors back together. So we'll get to that.
Right.
Yeah.
Okay.
So this is a picture of Galileo's telescope. I believe this is a reproduction in a German museum. These are two telescopes. Objective up here, they were about 1.5 to 2 inches in diameter.
Wow.
And a smaller lens back down here. Now,
I think those are in the Galileo Museum in Florence, in Italy.
Okay. This shows just what we were talking about, the dispersion of light going through a single. This is a plano convex lens. White light comes in here. It's dispersed into its two colors here, red and blue, that are different. It's also got all the other colors in between these two. And the image plane here, the blue focuses here and the red focuses here. If you look at the blue, you get this image in the blue, but it's surrounded by a red halo. If you take a crown glass here with its dispersion and a flint glass, give them this shape, which is a Fraunhofer original design for a achromatic lens to reduce color, you can bring the blue and the red to the same focus and you get this thing here. But and that's an idealization. Fraunhofer's actually had an air space in here. This is a cemented doublet, but there are more colors than just red and blue. So with two elements, you can bring two wavelengths to the same focus. And they've shown red and blue here. With three elements, you can bring three wavelengths to the same focus. And so that we'll get to that. So this is a unitron refractor. This is what was popular technology in the day in the 1950s. This is a 4-inch diameter telescope. It's f/16, which means it's very slow, and it's a very long telescope. And it's long to reduce color aberration, because when you have an achromat, you still get some color. And so you have to have a long focal length. With modern glasses, we can make this about half this length and still get a very good image out of it. And going to 3 layers. So this is a modern achromat. Two lenses up here, and you notice it's significantly shorter. This is an Orion 80 millimeter, so it's a little over 3-inch diameter, and it's f/7.5. The other was f/16. This is about half the length of that one, and it gives better color correction because it's using modern glasses that are called exotic glasses. They have more desirable dispersion relationships.
So those were the EDs, right?
Those are no longer available, but I have one. It's a wonderful starter telescope. They were $499 about 20 years ago.
Yeah.
You can still find them on the used market.
Well, you just said, Jerry, that long one was very slow. I don't know what that means.
Slow means the F number is a big number. It's f/16. A fast system is f/7.5 or nowadays f/4 or f/5. It's like when you have your camera setting and you go out in a bright sunlight with Tri-X film, you set your camera on f/11 because you don't want all that light in there. So it's slow. It takes longer. There's less light available. If you set it at f/2, you're going to flood the film with light. And you have to make the exposure time really short. So that's why it's called a fast system, because the exposure time has to be real short. So it takes less time to take a picture. So this is an achromat, which we've been showing in the Unitron and the Orion. It's 2 levels. This one is an air-spaced achromat, and it shows 2 different wavelengths coming to different colors. We now focus on 3 bands for almost everything in optics: RBG, red, green, and blue. And so this is the green focused here, and this is the red and the blue. With 2 elements, you have enough variabilities to bring any 2 wavelengths to same focus. This one unfortunately shows the green and the red. It's separate. It's usually the green because that's the one the eye is human eye is most sensitive to. So they usually combine this and the red one. And then in an achromat, if you see false color around a bright object, it's usually a blue or purple halo. And if you get a minus violet filter and put it in your system, then the achromat gives almost no color at all. But it's better to have one that's designed with 3 different kinds of glasses, and we have very exotic glasses these days, and that will bring 3 colors to the same focus. And these, so achromats are good for getting rid of color. Apochromats are even better. Technically, these 2 things mean the same thing. What is it? No. Anyway, they both
color.
color-free. Achromatic, apochromatic. They both mean color-free.
Did you say that there's air in between those lenses?
Yeah, you see the gap in there?
Why?
Why? It's part of the design. If you have air in here, then you can make these 2 surfaces, you can give them slightly different curvatures. So that gives you an extra degree of freedom for designing your lens. If it's a cemented doublet, which many are, then they have to be exactly the same curvature. And that is a constraint that takes away from your freedom of design.
Oh, never knew that.
You
Then
can
they have
also get oil
space.
gaps
Yes.
too, where they use oil with a certain refractive index.
Right. Okay, this is an Orion apochromat. This is a 3-element Orion. This is F5. It's a fast system, very fast. The other Orion, the achromat, would not give a good image if it were made F5. F7.5 is about as fast as you can make it, but it gives an excellent field of view. This is an excellent performer, wide field of view. But as the number of lenses goes up, the weight goes up and the expense goes up. So that achromat was about $500. This would be probably $1,400 for an apochromat. There's wide range in these things too from different vendors. And this one is what's called a Petzval design. It's 4 elements. And forget this element back here. This is a field flattener. But the telescope itself is sold by Teleview, and other people make Petzvals too. It's a 4-element design, and there is virtually no color in this lens. I have one of these in a 5-inch diameter, and Tim has one in a 4-inch diameter.
Yep.
Nogler Petzval.
I have one in a 75 millimeter diameter. That's my finder scope.
Yeah.
Pentax.
I had the predecessor to the Nogler Petzval, which is a shorter tube, and I don't know what mine was called, just 101. So
okay. That was I don't recall what that. I thought you had a NP 101.
No, it wasn't the NP. It was just a TV 101. So
well, NP stands for Nogler Petzval, and it's Nogler's design, Al Nogler, who designed wide field optics for NASA for a long time. And then he started his own company. Absolutely perfect optics, in my view.
And
no,
I think
really
Tim's
nice.
is an apochromat, so a triplet.
Yeah. Okay. Good.
No, it's a 4-element.
Oh, 4-element. Okay.
Yeah. The fourth element is a field flattener.
Yeah, that's
okay.
This element. So you have these 2, and then this, and then a field flattener.
Yeah.
Oh, okay.
That's an excellent telescope. But now we're getting into the stuff that amateurs like to make. And this stuff completely reflectors get completely around any color error, no chromatic aberration at all. The laws of reflection are not wavelength dependent. There is no dispersion in a mirror because the glass is never passed through in the telescope when it comes in. This shows a mirror down here that is a paraboloid. It brings wavelength, it brings light that it is a plane wave out here, so the rays are parallel. It brings parallel rays into a sharp focus at one place. And you see that this red line up here, which represents the focal plane, is flat. So it's perfect for putting a camera lens, a camera focal plane there, because it takes a picture without focus error. The active elements are this layer of probably 200 angstrom thick aluminum and 200 angstrom thick of aluminum on this mirror. The glass just holds the shape. The mirror is actually the optical element. And this is a Newtonian reflector. Now, Newton was the first to make a reflector of this type. Oh, this is a paraboloid. mathematical paraboloid. This is about f.5. You would never see a telescope with this much of a
Yeah.
But where we make is just down in this region. But you can see because of the shape, it's obviously not a sphere. And that the mathematical property is that the distance between a sphere and a point, or a surface and a point, is a constant. That is, it comes to a single focus in a paraboloid. In a sphere, if this were a sphere shape, it comes to a curved surface called a caustic. And so that gives spherical aberration. So, but all we do is when we make our mirrors, we make them to a paraboloid, so there's no spherical aberration. Now, Newton didn't know that, and he didn't have a good way to test his telescope. So this is the first Newtonian construction by Newton, but he actually used a spherical mirror back here. But, and he used a very small water droplet eyepiece, I guess, for the view. And he did have spherical aberration at this focal length, but it was a revolution in design. It had absolutely no color error. Now, this is the same thing that we use today. This is a Newtonian telescope. The primary is down here. It reflects up here to the secondary, and that reflects over here to the eyepiece focuser, which you don't see real well. It's in the bars. And this is lightweight and portable. These things can get fairly big now because the primary weight is in the mirror.
Looks like Albert High's design there.
Could be. It's just random off the internet, so it's no ones that I know. This is amateur made in my view. It does have a drive system down here, so it does try to track the star for a while, and I can see a little computer up here for a go-to system.
Oh, wow.
This is an Altaz mount, but it's called a Dobsonian mount. And there was a fellow in San Francisco that developed this type of mount as inexpensive, but giving you access to big telescopes and so you can see a lot of faint objects. It was John Dobson, and he had a club up there called the Sidewalk Astronomers in San Francisco. And he developed this type of thing, which has just exploded across the amateur world. You can get mirror diameters here easily up to 40 inches in diameter. They're called transportable, not portable. You have to sort of put them together on the spot. So,
I like that.
But it's pretty quick. One fellow I knew went to Steve Overholt, took his 30-inch Dobsonian to the Riverside Astronomical Society's RTMC, Riverside Telescope Makers
Conference.
Convention.
Convention
Conference
at Lake Arrowhead, and he had a 30-inch and he brought it there all disassembled in his little mini Toyota, one of the first Toyotas to come out, and he got an award for the largest telescope transported in the smallest car.
Was that the one they called the Yard?
No. The Yard scope was a great big 36-inch mirror, so a yard across.
Right.
Yeah.
And it looked like a railroad car. I mean, it was in this big trailer.
Oh, okay. Yeah.
There are these Dobsonians that are so high you have to get up on a ladder 10 feet tall to look through them. The eyepiece is high up. I have acrophobia, so I'm not getting near any of those telescopes.
David Schiffman was a mayor of Santa Barbara from 1971 to 1984.
Yeah.
And he had a very large reflector, because I remember it being at the museum during one of the star parties. It was in a big parallelepiped, a big rectangular box.
Mm-hmm.
And
Yeah.
the box had to be easily 4 feet on the side. I'm not sure how big the mirror was, but it was probably 30 or 40 inches.
No. The mirror was like 24 inches.
Okay.
And it
It
was
was a big box.
At the end, it was the box was termite infested.
Oh.
And the mirror did not have a very good figure.
No.
It was decent, but not great.
We sold it to someone about 10 years ago.
I remember David Schiffman. He was a little guy, but this sucker we're looking at never is inside an observatory. It's outside all the time.
Well, it's taken to star parties. This is what you go to these star parties like CalStar in the fall here in California,
No,
you
Ron,
set these up.
it's not outside. These are portable. They tear down, so they're not kept outside.
No,
Yeah,
they're
they
stored
come
in your
apart
garage.
into several pieces. You know,
Yeah.
the top of them comes off, all the tubes come off, and then the bottom is the mirror housing is a separate piece.
Yeah, it just folds up into a box. So you put it
Right.
in the car. They're made to be transportable.
Yeah.
Charles Schuler has a 20-inch like this that he brings.
Yeah, I
that
was just
he
gonna
packs
mention
into his
that, yeah.
car.
And then he put his is on a tracking mount too.
Yeah. So is this one.
Okay.
Well,
Some of
this
them have
one's on an
wheelbarrow.
Altaz tracking mount, but Charles has a Ponset platform.
Okay.
Well, for some reason, I thought all telescopes needed a tube to keep it dark inside.
No.
Yes, it
Well-
does if you have a lot of polluting light around it.
And the other thing they did here is this is called an open truss design. And so these trusses separated the upper cage from the mirror box below. But what people do is they go out and get a black fabric, and they wrap it.
They make a shroud.
Yeah, you
And
can
so-
cover this all with dark cloth. And here's a light shield up here, because when you're looking in the eyepiece, you're looking at this thing, but you have to look. You also get light that can come around this mirror. So you want to block that out.
Yep.
But they're intended to be used at dark sites up in the woods or something.
Yeah.
Charles always marvels at what good contrast that I get that he doesn't get. And I keep pointing out that the black shield isn't black. It reflects a lot of light. And you can buy black paint that's 99.9% absorbing. It's dark.
You can
Well,
also take dark black paint and you can mix sand with it, and that'll give a rough surface.
I've done that.
Yes.
I've done that, professionally.
Yeah.
In the optics that I made.
Well, I've seen some that are almost this big at our star parties.
Yeah. This is in the size range of what Charles Schuler has. I think you mentioned he had a 20-inch.
20-inch.
20-inch. Yeah.
20-inch, and Joe Doyle has an 18-inch.
That's right. Yeah.
Yeah. Charles bought the 20 versus the 21 because the 20 would fit into his car.
Yeah.
Tom Whittemore made it in 18.
Right. Yeah.
Hey, when I buy cars, I have to measure the trunk and back seat of the car, so I know I can fit my equipment in.
I buy Suburbans.
Okay. Now there's other designs of reflectors too that do not have chromatic aberration. This is a Cassegrain design, and here again we have a mirror that is parabolic to first order in the classic Cassegrain. It gives a field of view that is flat. It's good for taking images. The secondary mirror is rather a challenge. It bulges out, so it's hard to test. And it has to be hyperbolic, which means it's beyond, it has a conic constant over 1. So, which is not anything except just a mathematical curiosity, but it's the fact that it bulges out gives you a challenge in testing it. But once you get used to it, you can do that okay. The field of view, the magnifications are fairly high. The primary mirror here, typically in a classical Cassegrain, is f4. So that means the focal point comes out here at about 4 times the mirror diameter, which is this to scale. And once you do this secondary, this has the effect of magnifying the image. So you get something back here that is f16. So it's a high power system, very narrow field of view. If you don't have an automatic pointing system, it can drive you nuts trying to center on a faint object.
And you can see it has a hole in the middle of the primary mirror.
Yes, you need,
That's
right.
the same size as the area that's blocked by the secondary up front. So you don't really, it's not like you're losing anything. You're losing a little light, but
yeah.
And
The
the scope they
CH
originally had at Westmont, the scope that was in the first dome, was a design where you could switch out different kinds of secondary mirrors. So you could either run it as a Newtonian or you could run it as a Cassegrain like this.
Yeah.
But
And the Mount Wilson does that. They can, the front end bolts off and you can bolt on one that has a Newtonian side reflector, or you can just put a camera up here and work at the prime focus of the main mirror.
Well, they also can do an azimuth mount.
Yeah. We'll get to
the
those
end,
kind of things.
the end result is we don't get a big hole in the picture.
No, once it comes to focus, the hole is squeezed shut.
Is that right?
Yeah.
Okay.
Now this is
At the rate we're going, gentlemen, we may not get to the night sky, but this is fascinating.
okay. So this is a Dalkirkham, or no, this is, what did I say this is?
Cassegrain.
Yeah, no, we just did a classic Cassegrain. We're doing a few variations on Cassegrain.
Okay.
So this one is, yeah, we'll go back one. Let's see, right there to the classic Cassegrain. Now there is a variation on this that's made because the hyperbolic mirror, the secondary, is difficult to make, and so it's expensive to make. But you can make this by having what's called a Dalkirkham approach. It was invented in the 1930s, and that the surface mirror here is an undercorrected paraboloid, and the secondary is a sphere. It's very easy to make a sphere. So these become very inexpensive. Coulter Optics sold a lot of these things, optical sets in the 70s and 80s. A lot of people when they make Cassegrains, they're really making Dalkirkhams. The Dalkirkham also has a flat focal plane. It has perfect correction for almost everything right in the middle, but it is very narrow. So if you move a planet out to the very edge of a field of view, you can start noticing some distortion, but they're very inexpensive to make. Now this one also looks like a Cassegrain, but what's that?
Is it a Gregorian?
No, that's a Gregorian, would be a concave and a concave mirror. And I didn't include Gregorian into this discussion. It's a slight oversight. This is meant to represent a Ritchie-Chrétien, which is what almost all the major telescopes, the big boys play with on Mauna Kea and stuff are. Now it does have it has a much bigger hole in this back end, and it has a larger secondary. And this surface here is an undercorrect. What's that?
Hyperbolic also, right?
Yeah, it's hyperbolic also, and this is hyperbolic. So it's a fairly challenging one to make, and it's fairly challenging to align. But you see the reason that it's favored is it gives near diffraction limited circular stars over its entire field of view. But the field of view is curved, as you see here. So there has to be a field flattener put in here somewhere. And then it gives very nice star images over a very wide field. So that's what they use. And it's like the 30-meter telescope, when they finish that will have a segmented primary mirror, but it will be a Ritchie-Chrétien type thing.
And what they used to do without a field flattener is they would just curve the film.
Yes.
Yeah. They had a vacuum apparatus to do that, right?
Yeah. The what?
They had the vacuum apparatus. It was on a plate full of little.
Oh, that we're coming to that. Not on this surface. You can't bend these discs.
But
okay, Jerry. What Bruce was talking about was for curving the film, not for the corrector.
Oh yes. Oh yeah, you're right. Yes. Sorry, I misunderstood. You're absolutely right. They'd curved the film plane by sucking on it with a vacuum.
Wow.
Okay, this comes. These were introduced in the 60s. These are Schmidt Cassegrains. They're a version of catadioptric. So we went through refractor and then reflector lenses and mirrors, and now we have a series of telescopes that have both lenses and mirrors, and those are called catadioptric systems. This is a Schmidt Cassegrain. It has a primary mirror and a secondary mirror that are spherical, and it has a corrector plate here to get rid of the spherical aberration. It's a very thin plate of glass. This one kind of shows it 2 plates of glass, but it's not 2, it's 1. And it's got a little complex curve on it. But these are easily made because they form them on a disc that has vacuum holes in it, and they pull a vacuum on it, so it warps a very thin piece of glass. And then they grind and polish the glass flat. And then when they release its shape, it relaxes back to the exact complex shape they need. So they're very easy to make.
Good grief.
And so, and you see the primary is what moves back and forth. Here's the knob that you turn to focus it, and it slides the primary mirror along on a greased tube in the center. So the spacing, the resolution is very closely tied to how accurate you are in the spacing between the two mirrors. So when you space it so it has high magnification, that's the design parameter. And then to get lower magnifications, you back the mirror off and the resolution declines slightly, but you get a wider field of view and you don't notice the resolution being lost because you're at a lower magnification. So these things just took over the marketplace.
Is this the
I'll get lower resolution or a longer focal length by putting a focal reducer on the back of the.
That's an added on asset to it. I'm not going to cover those things because you can get all sorts of Barlow lenses and field flatteners. This is an 11-inch Celestron. I think it's an Edge.
Mhm.
Yes.
Yeah, Edge, which is their high quality one. You can see the secondary is held up. This is the secondary housing mounted in the window, the correcting window at this point, and you can see a little bit of the primary mirror back here. This is a common size. This is 11-inch, I think, and Meade makes a 12-inch boat anchor version. No, excuse me. The Meade makes a comparable thing. Celestron makes 11. They go up 16 inches. I think
I have their 9 1/4.
9 1/4. Okay, and I
think
we
have the 12-inch Meade at the museum.
Yeah, I was just going to go
there. We have a couple of those.
Yeah, right. 2 of them.
So they're very good scopes. They're easy to use, especially on mounts that are go-to. This is the popular thing because they're short, they're portable, they don't weigh a lot, and they give real good high quality. The native telescope is f10, which is fairly slow. If you want a wider field of view for imaging, you can put a field demagnifier on it.
Focal reducer.
Focal reducer, thank you. And you can get to an f6.3, which is very good for faint fuzzy imaging.
Well, also on some like the Celestrons, you can remove the front mirror. It comes out. And then when the Starzona makes a lens, you know, the picture that Bob Richard took of M42 was shot at f2 or f2
Yeah.
You get a very fast telescope by
it's very efficient with light, but in a place where you have city lights bouncing off the sky, f2 you'll fog up right away. So it's really a dark sight focal ratio. This is a version that is taking over the high end of amateur astronomy. This is a corrected Dalkirkham. This has the undercorrected primary and the spherical secondary, the ease of making it. It gets around the narrow field of view of the straight Dalkirkham by putting a couple of simple lenses in here that have no real optical power, so they don't magnify or demagnify. And you get a very wide field that's very high correction. Because the big observatories use Ritchie-Cretan designs, those became popular among wealthier amateurs. But then these corrected Dalkirkham, for example, offered by plane wave instruments, come in at about 1/3 to 1/2 the price of a Ritchie-Cretan, and they outperform them because they have a flat focal plane.
Is not the one that you're making this design?
Yeah, I've got one half built. So, and it may stay half built for a while.
So what diameter is that one?
14.5-inch diameter, f3 primary and an f7 secondary. So this is the plane wave instruments corrected Dalkirkham. The diffraction or the corrector lenses are in this housing here. This is the secondary spherical mirror, easy to make. The primary is easy to make. And this is a 14-inch diameter, and that runs about $16,000 delivered. It does not come with a focuser. You pay more to get a focuser put on it. but these are very popular among imagers.
Wow.
This shows a Meade version of a corrected Ritchie-Cretan, which is an excellent performing telescope, but they got in legal hot water with RCOS, who makes original Ritchie-Cretan telescopes uncorrected, and they called this corrected Ritchie-Cretan, and they got sued because they were using the name Ritchie-Cretan, which is a specific patented design, and they've
copyrighted probably.
Yeah, they both fought each other to a standstill, and they compromised, and Meade stopped using the word Ritchie-Cretan.
And I think they both went bankrupt.
I think Meade got bought by someone, and Arcos went out of business.
Meade got bought by Orion.
Yes, that's right.
Wow.
Now this is the last one we're going to look at. This is another type similar, but it's a Maxitoff. And you see, instead of having a thin corrector plate up here, it's got this massive piece of glass up here, all spherical surfaces. So you get rid of that complex shape that the thin one had to have. And it's a spherical piece of glass, but it's fairly thick, like an inch thick. And so this thing is very front end heavy. So they put a lot, when they make these commercially, they put a lot of heavy lead weight at the back end so that the balance point is closer to the back end than the front end. These are excellent for high resolution narrow field. They're called planet killers, Maxitoff. A number of places make high end ones. Teleview, maybe.
Astrophysics.
Astrophysics, that's what I was trying to think of, yes.
I have the Orion 127 millimeter.
Yes.
But the secondary mirror is just
there we go.
The secondary mirror is just an aluminized circle on the backside of the meniscus.
Yes, it can be. Yes. And this is a 3-inch diameter Maxitoff. These came out in the 40s and 50s. I know that, and these were way above the average amateur in the 50s. These were $999 or something like that.
Really expensive now.
Yeah. But this
and they made a 7-inch version.
They did, and they still do. This is all titanium. It's not machined out of steel. So it's quite an exotic, and it boasted like a 1/100th of a wave optics and stuff.
Oh, they boasted about the scene being really incredible.
Yeah.
They put a star map on the outside of it.
Yeah, this is a shield that slides up on the front. You can put a star map, or they sell one with color pictures of nebula and stuff on it. Wow. And everybody complained about the color pictures because you couldn't see that in these scopes. It was, this scope had too small an aperture to show all that color.
Well, it's more your eyes.
That's a brief review of telescopes available to the amateur and their history.
Wow.
They use really nice eyepieces too, Jerry. Brandon's.
Yeah.
These Brandon's.
Oh.
Yeah.
Oh, I didn't know that.
And Brandon's were made by Roland Christen.
Vernon Instruments.
Yeah. I've got 3 of them in my collection.
Yeah.
And he's the guy that started astrophysics.
These
really?
These eyepieces screw in. And then later, after other people wanted Brandon eyepieces, they made them with the slip-in 1.25-inch base so that people could use them in other telescopes. You'll also notice this thing sticking out the bottom. That is a Newtonian mirror, and you can slide this whole thing up, and then you still look through the eyepiece, but now it bounces off the mirror up here and goes through the front end. And this is a wide field finder, so that's the finder scope for it. And then you slide it down to look through the main telescope.
And that's the Questar Maxitoff.
Maxitoff, yeah.
Maxitoff. Wow.
And Roland Christian, is it Christian or Christensen?
Christen.
Yeah, he was the guy that did astrophysics.
Yeah.
Yeah. Still does.
Interesting.
Well, can you possibly summarize the rest of it? We're going to have a good seeing this Saturday night if we don't have weather problems at our star party, don't we?
Yeah, I don't know what the weather's going to be like.
Yeah, well,
it's looking like it's going to be better. So it looks like we'll get away with it.
Okay, good.
Friday afternoon, new moon, right? think
Yeah,
it's Friday.
and Chinese
right.
New Year.
Oh, no kidding. Which animal?
Dragon.
Oh, that animal. Okay.
Okay, well, in Auriga, you can find NGC 1931, which is not this bright spot. It's this dim circle right there. It's a nebula that has in it these structures, which then gives the whole nebula the name the tadpoles.
Uh-huh. Tadpole.
And then this is a open cluster in the nebulosity.
Can you see this in our 8 or 11 inch or 12 inch scopes?
That I don't know. You can see it in a 14 or 16 inch. If the
You
sky
could probably photograph it, but
you
visually it's probably
photograph it.
tough.
Yeah, I think if you have a 6 or 8 inch, you can photograph it.
Tadpoles are in there somewhere. Okay.
And then we have
This is hopeless for us.
this is a last minute object. This is Comet Pons Brooks, and it is in Cygnus, which is right on the horizon at dusk. So you got to be up in the mountains in a very dark site. But if you want to see the comet, it is now 8th magnitude, which means you still can't see it with your naked eye.
Is it coming in or has it gone around the sun, you think?
It's coming into the sun, and it's as close as it's going to get to the Earth.
So we can't see it Saturday night for sure.
No.
And whoops. And then
We'll probably have a building in our way on Saturday night.
The final thing is, it doesn't say what it is.
That's the crab there.
Yeah, this is the Crab Nebula it's a drawing of what it looks like visually to this guy. And he drew it in 2004 with a 6-inch f8 Newtonian. And that's about what it looked like in my 6-inch f8 Newtonian back in the 60s. Sirius Plossel. So, that is, let's see, what do we got here?
The swan, you got the swan.
Yeah, that's right.
Yeah, you wanna go back to Taurus.
Yeah,
but this is Sagittarius now.
Right.
Yeah. So this is the Swan Nebula, which I list in my talk. Here it is. Sagittarius, the teapot, and the smoke coming up. And M17 is one of the many, many clusters and faint fuzzies you see coming up in the summer sky.
So that's pre-dawn now.
Yeah, it's pre-dawn or the evening in the summer.
Oh, this is the one that we saw out there at Bacara. Chuck, you were out, you and Pat were gone, and that night was just unbelievable.
And this is called the 2 Nebula. or the Swan. It's very irritating that it's been for a long time called Omega Nebula, which implies other stuff out here that you can't see. And this is a amateur photograph, but you can see it's heavily vignetted around here. So he needs to do his flat field correction better.
So we'll get to.
I've got a real good photograph of this with my 127 millimeter Matsutov.
Okay. Well, let's look at that next week.
Yeah.
All right. We'll probably have to move 4 Vesta, the asteroid, to next week too, I guess, unless you covered it here and I missed it.
No, we didn't cover it. It's
covered, but I didn't mention it.
Yeah.
That's okay. No problem. There's a lot going on, not the least of which is the weather, gentlemen.
Yeah,
and
this is.
Go ahead. This is what?
M1.
Oh, there it is. The asteroid from hell. It'll on us someday, according to Neil deGrasse
And
Tyson.
M1 is that green blob.
Oh,
yeah.
Well, gentlemen, take care of yourselves and your scopes. And by golly, let's do it again for number 156 episode next Monday morning, 11 a.m.
Okay.
As we continue to assemble here, and we'll get ready for Saturday night. There's a Saturday afternoon meeting, and I got a couple things I'm going to bring up. You're all invited to log in. And thank you very much. We're getting ready for our 4th year, so we'll see you next week on the Santa Barbara Astronomical Unit SBAU Astro Hour.